Thanks a lot, John. So it would be quite a short talk. It's about 30 minutes. And the road map for my talk, it's a kind of story, actually, because when I start working with functional data, and then I joined Chris Podgorski for his to be a postdoc, and we want to do something for functional data. And every time they say about functional data, splines is like somehow the first nomination. And we were thinking, oh, we should do splines, but splines, they are not orthogonal. So that's maybe one thing. And when we start, okay, let's find what people do in functional data and how can they orthogonalize those B-splines. So we start, to find how can one orthogonalize B-splines. And then we found that, I would go through that. The classical orthogonalization is somehow missing something. We didn't like it. And we start then to find, okay, how can we do a better orthogonalization? And then we extend it to somehow called periodic splines, where the splines are on circles. And then we extend it again with Yetka and Ivana to specific kind of Z-spline, they call it. And at the end, I will tell you about our package. So as you have seen yesterday with Tom and many, just the splines, you have some kind of set of knots, and then you build your splines bases and the degree 0, and then you have this recursive formula, which is very nice and easy and very handy. But then we said, okay, if we want to orthogonalize those B-splines, so it's more mathy here, but it's, if we just do the inner product between these splines and themselves, so we get this Gramian matrix, which is H. So if you just imagine I have a set of spline, and then I have multiplied the same. So I'm taking the inner product of each themselves to get the Gram matrix. And this Gram matrix, of course, it's not orthogonal because the B-splines, they are not orthogonal. So the question is, can we find such a matrix P if I multiply it with the splines? So more or less, I'm orthogonalizing those B-splines. So we get the identity. So this is the math behind. So if you like math, there is some math behind, but I will not go to the math. I will go more for applications. So whenever you say about orthogonalization, the first thing we got in our mind, Gram-Schmidt orthogonalization. It's the most popular way. And you say, okay, let's do that. And on the right, you find the B-splines. And on the left, I will show the orthogonalization. But Gram-Schmidt, if you just forgot for any reason, you start with the first element, and then you take the second element, orthogonalize it with respect to the first. Then move to the third, orthogonalize it with respect to the first and the second, and etc. So this is exactly what you will see here. Hopefully it will work. Yes, so you get the first splines, and then take the second, orthogonalize with respect to the first, the third with respect to the first and the second, and to the end. If you look at this, there is one thing we didn't like with this orthogonalization, because every time you go, the support of those splines getting bigger and bigger. So the first one gets the same support, but the second gets bigger support, and the bigger and the bigger, and the last one, it gets all the interval. That's what we didn't like, because we lose the locality of the B-splines. So we were searching, okay, can we do better? And we found one paper for Simon Reed, and it's called two-sided orthogonalization. It's more or less Gram-Schmidt orthogonalization, but they split the B-spline, the bases we have, into two sets. So they start orthogonalizing from left to right and from right to left until they meet in the middle. So it's also nice, but again, we have the same problem. So let's see how they orthogonalize. So that it's like, it keeps the symmetric. It's very nice, but still the support growing. And we lose the locality again. But it's nice because we have the symmetric. So the splines is still also like aligned with two sides. But also we've lost the locality of B-splines. And so that's our conclusion after maybe 6 months. So we were working and searching, reading papers, and we found, it's nice. We get somehow orthogonalized bases, but the support of the orthogonalized version of B-splines getting bigger and bigger. And also we lose the symmetric, we keep the symmetric if we use the two-sided. So we were searching, can we do a bit nicer? So one nice result we found, it's very old math result. It's somehow, if we have two symmetric elements and we want to orthogonalize them, you can orthogonalize one with respect to the other, or this one, the first with the second, or the second with the first. But we want to keep the symmetry. And we found this nice result in math book. So if we have two elements, x and y, they are symmetric. And if I want to orthogonalize them, I can use this formula. And by this, I get an orthogonalized version of x, orthogonalized version of y. So if I take the inner product of them, it will be 0. But the good thing, they still symmetric. So x tilde and y tilde, they still symmetric. We like this, but it's more or less similar to what we have in two-sided. So we cannot generalize this for many B-splines. But we kept this idea in our mind, and we like it. So we came and said, okay, but I mean, the first idea we got, it was from B-splines of order 1. Because order 1, if I have the interval 0, 1, so if I have many nodes, so the B-splines of order 1 are just triangles, like this. And if we look at every second spline, so if I look only the first, with the third, with the fifth, and etc. So those, the first and the third and the fifth, they have disjoint support. So they are by nature, they are orthogonal. We don't need to do anything for those. But then we still have the second, the fourth, the sixth, and etc. So we need only to orthogonalize every second one. And we got inspired by this small idea, why we do somehow, we build our net. So it's a kind of pyramid. And just to adapt for different degrees of our splines, we decide, okay, let's build somehow tuplets. So we divide our splines to many levels. The first level, the base one, we divide them to different tuplets. It depends on the degree. It's our choice. Don't ask, but it's our choice. I mean, you can have different tuplets, but I mean, we found that's maybe the most elegant one. So we divide, so we take the first 3, because I mean, I have cubic splines here. So I take the first tuplet, which consists of 3 splines. The second tuplet, it's also 3 splines, but they have this joint support. So this one and this one, they don't have anything in common. The same, I continue until I cover the first round of my tuplets in the base one. I do the same on the second level, but now I need only to cover the ones I missed here in this area. I wanted also the condition they have this joint support. So I cannot have the ones here because they have somehow a common support. So every time I go up one level, I build some tuplets where we don't have any joint support. So that makes sure, exactly as we had in the first order B-splines, we don't have any joint support of our splines. This one, I can easily orthogonalize using the theorem we like. So we want to use that theorem. So we said, okay, why we don't orthogonalize those two? Because they are very symmetric. We orthogonalize them with respect to each other to be symmetric, and then orthogonalize this one with respect to the other two. So we get somehow nicer representation of B-splines, but the support of these tuplets is just in that small interval. So in that aspect, we preserve the locality, more or less. And then we go to the second tuplets, and to finish the first level. So our algorithm goes level by level. After orthogonalizing the first level, we will go to the second level. And the second level, this one has nothing to do with the rest, only with those two. So I have only to orthogonalize the top ones, the second level, with respect to the ones they have joint support. And the same for that one. I can get. And of course, I should not forget to orthogonalize them with respect to each other every time. At very top, we have one triplet which has to be orthogonalized with respect to those two and to those two only, because it's somehow very disjoint support. So that was our idea for orthogonalization. It seems quite, maybe, I don't know if it's simple or complicated, but when we implemented, we found it's very elegant. So again, so this is our levels. So we start with the very bottom. We orthogonalize those tuplets with respect to each other. So we got almost half of our splines orthogonalized in a simple just computation. So we don't need to do a lot of inner products between the B-splines. So we got this one orthogonalized. The second level, orthogonalized with respect only to the two bottoms. They have joint support and with respect to each others, and the bottom one. And that's our splinet. We call it splinet because it's somehow, it's kind of net. It's better than just look at, it's like just a consequence of, or a sequence of splines. We build it as a pyramid. So after we got this one, we were quite happy with that one. But we found that if we use only B-splines, which is very nice and local, and the support is almost of the order of the interval length. So we call it of order 1. While in Gram-Schmidt, it's of order n divided by 2. So the more knots you have, the support grow. And the same for 2-dimension, it's half of it, so it's n divided by 4, while our splinet of the support grow of logarithm, log n. So it's a bit kind of reduction. And if we have too many knots, as you can see from the graph, it's more or less get somehow quite stable. So that's one type of efficiency we found in this algorithm because it's preserved the locality. The other type of efficiency we were measuring as well, how many inner products we have to do. Because, you know, if I want to orthogonalize with respect to Gram-Schmidt, I have to do many multiplications. And Gram-Schmidt, we call it sometimes one-sided orthogonalization, actually. So the number of inner products we need for orthogonalizing B-splines of order k, if we have n different knots, it's somehow of order n times k. So we need to do n times k different inner products and some subtraction, while for our splinet, it's still of order n, but subtracted with log. So also we get some reduction with the efficiency of doing this orthogonalization. Yes. Any questions so far? Because I mean, that's the main things we have, I mean, for the splinet. Yes.
Does the support in somehow the average support because the support is different? So it's support on the splinet. I think the different levels get different support size. Counting here is somehow the average support?
No, it's the sum of all the average, as I remember. You can correct me. Total support, yeah. So the total support, the sum of all the supports. So the support of these ones plus this one. Plus, so the sum, yes.
Because I think when you go to the next slide, and the last figure, the last instance of this
exists, yes.
I think the last one is globally supported.
Yes, yeah. But I also must say that we found that we can do some small approximation because if you look at the top level, it's almost, yeah, so it's very local. Exactly. So, I mean, we found somehow an approximation if you accept some error. So if you don't want everything to be perfect, you still get somehow very local and of order 1, actually, as exactly as B-splines. So the support is, yeah, but I mean, I will come maybe to that, I mean, later on, but if we accept some error, we can just neglect the sides of the top level or many levels we have. Then we can, I think we found that we need only 3 levels at most for orthogonalization if we accept that error. Otherwise, you can grow to up. But if you look at that, it's very preserving the locality of the splines. Yes. Yep. No, but I mean, for only illustration, we have it equidistance. You can, yes, so you can have it any that exact. So Chris will tell more about that one. Yes, exactly. So the number of levels, it's the log of 2 of n. So so if to have like perfect dyadic things, we call dyadic things. So it's n, it should be to 2 to the power n. N is the level. I think it's n minus 1, as I remember. But of course, I mean, we don't restrict this n to be exactly as of this type, because we can do the orthogonalization, whatever n, we can approximate it with the nearest log of 2. Yeah, so I mean, that's the number of levels. Yes, sorry. This one. Yes.
So the second class, so with respect to the previous one, in addition,
Sorry, again.
we have a slight increase.
Where? In? Yes, but I mean, it's subtracting log of n. So for little n, yes, I agree, but it's, yes.
So the message is basically that it's not worse. That it's not worse.
Okay, it's not worse.
If you buy that, good.
Not that worse.
It's not that worse, yeah. So I mean, it's, I mean, the more benefit, I mean, we get the most benefit we get, it's the locality of the B-splines.
There is also this work of Pavel-Bosny or Orthogonalizing. How does it compare?
I didn't get the question, sorry.
The work of Pavel-Bosny and whose article of Pavel-Bosny about Orthogonalizing.
Okay, I don't maybe I haven't seen that paper. Maybe we should, yeah, take it. Yes, I will look at that. Yes. Any other? Yes. Yes, coming later. Yes, yes, yes. Any other question for this time? No. Okay. So after we got to that level, we were quite happy with this result, and we were thinking if we want to do something which on circle. So if we have data which is like wind data or whatever type of data, which is kind of circle, and we found that yes, one can do that. So the only condition different from previous, that if I have the set of my knots, the last knot and the first knot should be somehow coincide. So I get back to the circle. So I have other figure. So that's what we were thinking about this periodic splines. So if I start with that point and have some other knots, and then the last knot should coincide with the first one. And how can we build this B-splines on this one? So the idea we had that similar to the main idea we have in B-splines. So we usually add k, like I mean exact same knots at the very left and the exact same knots on the right. But here we said, okay, no, we will not add if you just think about 0 and 1. So as Tom said yesterday, so if we have 0, 1, so you add, depends on the degree or the order of our splines. We add many similar knots here and there to build our B-spline bases. But we said, okay, no, we will not do the same, but we will extend our interval where we just take repeating the first k knots from the left and put it here, and the same the last k knots and put it first. So it's like copying the first k and put it for the opposite direction, and copying the last k knots and put it on the other direction. So that's, I mean, we make sure that if I build my splines, it will be identical. So we don't lose anything. So that's what we did. So we just expand our interval with what that was for of degree 2. So we added 2 knots from the right, 2 knots from the left, but preserving the same distance from x0 and x1, it would be added to x7 and the extra 1. So it's exactly preserving the distance, so we can produce the same splines. And to orthogonalize those B-splines, we said, okay, let's, if we get back to the previous. So since our interval is only between x0 and x7, then I take only the parts of the splines which is on this interval, and then just kind of glue it so it doesn't harm anything. So for orthogonalization, for this one, we do exactly as we have in B-splines. We do it as different levels. We orthogonalize as before, but we still have the last level, which is to complete the circle. So that's what we have it on intervals. But if we represent them as on circle, so also we plot them on different levels, but of course you can have them as one level. You don't need to have all the time different levels, but only for illustration, we make it as different level. So the very wide circle, it's the bottom level, and then we go up and up, or like inter with higher levels. And this is the B-splines, and this is the orthogonalized version of these B-splines. We didn't like, one thing we didn't like in this one, that we are all the time cutting. If I get a circular data, I have to choose a point where I cut and make it somehow an interval. Because if I choose different somehow knots or different cut, it might get different B-splines depending on where I'm doing the cut. But if you keep all the time as 0 degree somewhere here, you get all the time the same. But that's the only thing we were, hopefully we can get something better, but so far we like it to that point. And then after we get to that point, we met Jitka and Ivana and Olomouc's people in Czech Republic, and they had one type of splines, they call it Z-spline. And that Z-spline is somehow useful whenever you want to approximate density functions. And I will not tell more because Jitka will tell tomorrow or Thursday about this one. But the main idea that they want to build some splines, which if we integrate those splines to be, the integral is 0. And that Z-spline is doing that. But that spline has very easy definition. It's just the derivative of B-spline. So if I take the derivative of one B-spline, you get Z-spline. And it's somehow 1 degree less, because if you take the derivative, we lose 1 degree. And we were thinking, can we do the same here? I mean, for orthogonalizing those Z-spline. And we ran so if we start with B-spline, take the derivative, we get those Z-splines. And the orthogonalization, it's exactly as we have. But when we ran this algorithm here, I had in mind that those, even though it's Z-spline of order 1, but they are coming from B-spline of order 2. So just to keep the algorithm or our package consistent, so I just make a tuplets of 2 splines instead of 1 spline, just to keep the consistency of our package. Of course, you can do it in different way, but just to make it easier for ourselves when we write the code. So we found that our algorithm is quite stable and it can run for any types of splines. I just found that, there are many of you works with different types of splines. Maybe we can orthogonalize them in this way. And our package, so I still have 5 minutes. Our package, so it took us ages to make this package, but it's now online, or like it has been like for 2 years. I can just say about this package shortly, because Chris will continue on that. Most of the packages, they save splines as the coefficients of the polynomials. So they save A0, A1, A2, and AK. What we have been doing in our package, we said, okay, no, we will do Tyler expansion, because Chris had this idea that Taylor expansion is a better way of dealing with piecewise continuous splines. So we were saving the derivative up to order k and at each knot. And that gave us somehow the freedom to do derivatives, to do integration, to do many different operators. And so this is how we write our splines in our package. So it's not, if you just type, you will not get somehow coefficients, you will get a matrix of the derivatives at all the values at up to order k in all the nodes. In the package, there are many functions or many operators you can run. I think B-spline, one of very nice operator we have, so you can, if you have any type of spline, you can evaluate and you get the values as just many points. Of course, Gram, you can do some math, but I think there was evaluate and project. I think project function, that's very useful if you have functional data, because I mean, the main idea we had behind this work, it was applied to functional data. So if you have just a discrete version of your data and you want to project it to B-spline, so you have for this project function, you only need to give the nodes, the degree of splines and the data, and it gives you the projection directly. So it's quite convenient. It's available online. You can get it from this RCRAN, and that's my end of my story. Thanks. And that's some reference. Yes. Okay, to the code, yes. So it's available on CRAN.
On GitHub, right?
On GitHub as well. Sorry? She just asked about the code. Yeah.
So just as a remark,
yes,
there's a completely different way to orthogonalize these lines without changing the basis,
okay,
but changing the inner product. Right?
Yes.
You can choose a special type of orthogonal inner product.
Yes.
So that the standard basis becomes orthogonal.
Yes, but then you change the space. Because if you change the norm, you change the space.
The spline space itself is
yes, it's still the same, yeah.
The norm with respect to which you want to optimize
yep.
the approximation error is now a different space.
It's a different space, yes, I agree. Yeah, but that's very, thanks for the comment. Yeah, yeah. Perfect. To what? Sorry?
Okay, here. So, standard for each interval of the nodes. So you have your function, which is represented as sum of this line.
Yeah.
And that's converted in this polynomial form.
When we evaluate, we didn't use that form. No, we use only Taylor expansion. So we don't use this form at all. So that's most of our spline packages, they do this way. But in our package, we don't do any type of that one. We just do Taylor expansion around the nodes we have. So it's more or less similar, because I mean, if you just expand this one, you get x to power 0, x to power 1, x to power 2, but it's expanded around this node. I hope that makes sense.
And so, how do you get your
I mean, if you look at this one, how can you make derivative of this one? If I want to take the derivative, I just need to take r, multiply it here, so it will cancel this one, correct? So okay, it will do math, okay. It's simply, you just remove the first column.
How do you get this matrix?
How we get that one?
So the
Depending how you start.
Yes.
You start with the data, Then you project and you get this matrix. If you
Project
start,
means you go this way, or does it project?
this the sort of normal basis of spline that we probably spline that with
Okay.
L2.
Yes. Yes. Sorry if I don't answer your question. So
No, but that's
yeah, I think yeah.
Do you have figures of the sparsity pattern of the framing matrices?
Yes, we have in the paper. I didn't include it, but I thought maybe yes, but I can show you. I mean, in the break.
So,
and if you use a sparse solver, is it really faster than the standard?
That's what we found actually, because we applied for sparse data sets for functional data, and that's what we found it's quite useful. Yeah.
I would say the following for data analysis, that if you first orthogonalize, and then all data projection with orthogonalized space, it's faster because it's only once. If you want later on, with each function and account for lack of orthogonality, then it's slow, right? So especially for functional data analysis, this orthogonalization speed ups things because you do it once for all data for whatever you're doing.
Yep.
Okay.
Thanks.